All right, so we continue our session. We're shifting gears a little bit from small x to related topics of TMDs and PDs. And the first speaker of the second half of the session is Francesca Hautmann, who will talk about TMDs from low to high energies and Parton Branching.
Thanks. Thank you to the organizers for having me here. So here is the subject of my talk. I will say a few words on this. Transverse momentum dependent Parton distributions are defined from correlation functions of quark or gluon fields at non-light-like distances. So the distance y has a light component, a transverse component. The TMD is defined from a Fourier transform in y minus and yt of this correlation function. And there are known evolution equations for these objects which apply each in a specific kinematic regime. Here are two examples of evolution equations. One that is valid for low transverse momenta, for instance, Drell-Yan production in the region where the vector boson transverse momentum is small compared to its invariant mass. It's the CSS evolution equation. In the region of high energy, for instance, inelastic scattering for energy is much larger than the momentum transfer. You have PFKL equation or some variant of it like CCFN evolution equation. So they are defined by logarithmic accuracy, different logarithms in the two cases. Okay, so I should say the TMDs involve polarization as well. I will concentrate in this talk on the unpolarized distribution. Now, these equations like this are valid, as I said, in a specific kinematic. What I will want to do in the second part of the talk is to describe an approach on which I've worked with these collaborators, which is we adopted the Parton Branching approach, which is essentially motivated by wanting to have a description of TMDs which is valid over as broad as possible kinematic range. And which is valid not only for inclusive observables, but also for exclusive observables, so with a view to implementing it in a Monte Carlo benchmark. So the outline of my talk, I will start with an introduction on the TMDs in the two sort of classic regimes of high S and low QT, where they have been studied. Then I will describe the main idea of the Parton Branching method, and then some results and applications that we are currently working on. So to begin with TMDs at high energies, suppose you consider production of heavy flavor in lepton-hadron collision, so say electroproduction of charm, and suppose you consider the regime in which the energy is large compared to the heavy quark mass, which in turn is taken to be considered to be large compared to lambda QCD. And you ask, what is the asymptotic behavior in the high energy limit of the cross-section for charm production? The answer was given a long time ago. It's given in terms of a gluon TMD, which is denoted by A of C and KT, this formula. There's a factorization formula, which is given at fixed KT, and the gluon TMD satisfies the PFKL equation. Here is the asymptotic behavior for the gluon TMD. You plug this into this factorization formula, you get the high energy asymptotics of the cross-section. The high energy asymptotics of the cross-section look like this. There are factors in asymptotic behavior in energy or X is controlled by the scale intercept lambda. The behavior in the hard scale M is, I've taken this, the asymptotic value which comes from the FPL. It's in general an anomalous dimension gamma. I've taken its asymptotic value half. And then important is a function h, which is plotted here versus the anomalous dimension gamma. So this embodies the resummation of high energy logarithms. It comes, the function h is defined by this integration. As you see, it's given by an integration over transverse momenta. That's the reason why in the high energy limit you need transverse momentum dependent distribution. So the plotting this function h and evaluating it at the asymptotic value of the anomalous dimension is a way to determine how big the resummation effects are. So one will ask, say, if I take a very future deep inelastic experiment, will I be near the value at which gamma saturates, or will I be closer to zero? Correspondingly, will the resummation effects large or small? Mostly what I would like you to take away from this slide is that there is a definition, there is a need for transverse momentum dependent distributions, which comes from the high energy asymptotics. To do realistic calculations, people have supplemented the FKL, say, with finite X effects, subasymptotic terms. That's what leads, for instance, to CCFN evolution equations. I will not talk about this further in this talk. Or you can go in another direction. We heard about it this morning. You can include high density modifications of this, then you go towards nonlinear evolution at high energy. On the sort of other extreme side of the low energy, low transverse momenta, you also observe the need for TMDs. If, for instance, you look at Drell-Yan production at transverse momenta low with respect to the invariant mass. Then again, you have a factorization formula for the cross-section, which depends on transverse momentum dependent Parton distributions, this A and J. Here the formula is written in transverse coordinate. So B is the transverse coordinate conjugate to the transverse momentum of the vector boson T. And the evolution equations are different. It's an evolution, it's actually this region is a region which, as we saw in the previous slides, involves double logarithmic perturbative corrections. Correspondingly, you have two evolution equations in rapidity and in mass, unlike the high energy case, where the effects are single logarithmic. By doing this, you are able to take into account the logarithms of Q over QT. So it's, as we see, it's a completely different structure of the evolution. It's quite remarkable. It's the same object. It's a Parton correlation function, not like distances, that controls this completely different evolution structures and kinematic regimes. What this does for you, it gives you essentially the physical answer for the vector boson's QT spectrum. So this is, if you were to calculate the vector boson QT spectrum in fixed order perturbation theory, at leading order you would find that at the low QT end you find an unphysical divergence. If you said, okay, I calculate the next to leading order, you would find that the result diverges also to infinity, but with the flip side. You could even push it to the next to leading. You would find again a divergence plus infinity. The physical behavior is something like this, with the peak and the decrease, and it is only achievable if you use the approach, if you use a transverse momentum dependent factorization and Parton distribution. I should mention that become relevant in the second part of the discussion, that in a sense, when we use parton-shower Monte Carlo generator, we effectively do something like this, right? But only effectively. So with limited accuracy, and in particular in a way where it is difficult to control the logarithmic accuracy that one is implementing. What I would like to stress, this is the classic case of Drell-Yan, lepton pair production. What many people are thinking about is, what if I look at the same kinematic region, but for production of jets or heavy quarks, so colored objects? Does the same formalism apply? So to discuss this, it's perhaps useful to sort of decompose your TMD, which is a function of V, transverse coordinate or impact parameter conjugate to QT, and the hard scale mu. Decompose it as I've done in this way, as most people doing TMDs nowadays do. So you decompose it according to the region in transverse momentum along the initial state cascade. So you have a term which is purely the ordinary PDF. It comes from KT small compared to the momentum scale set by V, 1 over V. Then you have an evolution kernel which comes from the contribution of transverse momenta of order 1 over V. And then you have a Sudakov form factor which gives you the component of the evolution from 1 over V to the hard scale. Now, with this picture in mind, what I'm doing here is essentially an OPE on the TMDs. But with this picture in mind, you can compare the case of lepton pair production and jet or heavy quark pair production, right? So here's the decomposition I just gave you. This is my TMD decomposed into the ordinary PDF times matching coefficient times a Sudakov. I do the same for jets. And what happens is, in some sense, quite natural if you think about it in this form, because these final states now carry color, it's not just enough to have these blobs. You also have soft-gluons coupling initial state and final state, what are represented by this green blob. So these are potential long-time color correlations, which are never present in the lepton pair production case. These are the correlations which have been dubbed factorization breaking. They look something like this. If you write the effect of this delta, it's a trace over color which entangles these different factors. Okay? And delta is this blob.
So it's like a soft factor in forward.
Soft-gluons that connect.
So if I think of it in terms of Wilson lines, I think of it as forward Wilson lines.
Yeah. It's mainly non-perturbative. Is it non-perturbative factor?
Well, it has both components. Right? It has both components, right? Mm-hmm. In perturbation theory, the thing is it appears at fairly high orders of perturbation theory. So you don't see it. It also depends on the specific process and also what you're looking at. But typically, you don't see it at leading and next to leading order. It appears beyond the next to leading order to see effects of these soft-gluons. I don't want to get too much into this, not into this detail. I want to present it as a motivation. So there are potential new color correlations, which are hard to see in perturbation theory, so typically they are small effects. But they are in principle there. In some sense, if you think about it in this term, you understand that the CSS factorization is essentially almost always broken. So the exception is the case of Drell-Yan or Higgs, say, where you don't have color in the final state. But otherwise, it's you have this color correlation. They can generate simultaneous correlations. What people are discussing is, are these effects something that sits only at small transverse momentum imbalances, or could they be present also at imbalance scales large compared to non-QCD? Yes?
Francesco, on these specific effects and factorization breaking, is there anything published?
Yes, until now, so the next slide, I wanted to show one result. Until now, essentially, there was no detailed analysis or quantitative evaluation of how big these are, and people thought, well, they're typically big and confined to small transverse momentum imbalances. So this is a study which of heavy quark pair production, in which essentially the authors attempted to quantify these effects within a certain approach that would take more time than I had to explain. But essentially, the three curves that you see here are the curves in which you have, let's say, roughly speaking, initial state emission, final state emission, and then the effect of this correlation for the soft-gluons coupling initial state and final state. And so to see these effects, you have to look at the blue curve, and you see that the blue curve gives you an effect which is not small. It's of the order of 30% around the peak for the heavy quark pair. Okay, so this is, in a sense, it's interesting and to some extent surprising result. It points to the fact that these effects could also be present at scales which are significantly larger than the boundaries. Now, there is a slightly unsatisfactory situation because if you these things have been measured at the LHC, for example, right? The TT-bar spectrum. If you turn on the Monte Carlo, Parton-shower Monte Carlo, the scenario becomes a lot soggier. So this 30%, it's very hard to see. You do need Monte Carlo to do realistic simulation, to do realistic comparison with data. But on the other hand, well, we know that current Monte Carlos certainly do not contain such correlations. They're way beyond their accuracy, however you estimate. And yet, yes.
Sorry, would it be similar for a BB bar, a TT bar, or it would be very different? No, you change the mass.
No. So it would be present. It would be present in all of them. It would be present, but I mean, this is in some sense more striking because, well, it was an idea that these effects would go away.
Very high mass.
But they don't. So one might think that if they're there in the top core case, certainly. Yeah.
Just, I mean, kind of very effective theories of QCD where high accuracy can be achieved, such as soft-gluon effective theory. And of course, their factorized expressions include jet functions, beam functions, and soft functions. Part of the name of the game is to calculate precisely those correlations. Of course, an effective theory framework. So I was wondering, is this something beyond, or are we kind of talking about the soft functions in a city which have been included?
No, what we're talking about is this, right? So in the soft, so the whole CSS framework, so the whole CSS framework has been recovered precisely the same in the soft collinear effective theory. Soft collinear effective theory gives you just the same for the standard case of Drell-Yan. So I'm not aware of detailed studies of in the case of, for instance, azimuthal correlation for production, but same.
That's one specific case, I would assume.
But that certainly can be studied in the soft collinear effective theory, and so the language is different, but the physics is precisely the same. So, yeah. Yeah.
Francesco, this final state
Yeah.
is exactly what Rogers and Mulders looked at.
Yeah.
And they also spoke about factorization breaking, but due to different types of graphs. So actually, the interaction between remnants from incoming hadrons and the active partons. Now, I'm not saying that these type of effects cannot break factorization. I'm just wondering whether, if you look at the data, how one can really disentangle the source of.
No, it is. I mean, as far as I can see, is way beyond the current status. I mean, certainly there are different sources, perturbative and non-perturbative. So Mulders has thought already a long time ago about in terms of operator structures and arrived at the statement of factorization breaking and non-perturbative sources of azimuthal asymmetries. This particular calculation showed that you can generate a non-perturbative asymmetry, an azimuthal asymmetry by purely perturbative graphs, if you go at least to the next one. But so I agree that there are different sources. Yeah.
So,
Yeah.
first finish the sentence.
No.
But Francesco, a long time ago at Hera in SUS,
Yeah.
they have measured basically what I would call the Kahn effect based on gluons, which is a higher order effect, exactly kind of generating this kind of cosine moments. So is this now beyond this? Or is it only because it is even higher scale that it is surprising that it survives?
No, I'm not aware. Measurements by H1 and Zeus, you say.
So at SUS,
By H1
which measured basically what we call, if we talk about TMDs, the Kahn effect, which is, and they did that for gluons, so that gluons give you a cosine phi moment basically in your distributions. And Lucia, for example, simulates that.
Okay,
I can show you.
Yes,
we can
yes,
maybe
yes.
talk about. Okay, fine. Good.
I don't know enough about this particular measurement.
Good,
Yeah,
good,
yeah.
good, good.
Okay. Okay, so what I view this as a motivation in the sense that, as I was saying, I think to do comparisons of theoretical predictions with data, one needs to implement the theory in an event generator. And as soon as you do this for these observables, you find that the scenario becomes a little, definitely much less clear. So this was partly the motivation why I want to talk about the Parton branching method, which is a way to construct TMDs in a way which is valid not just at inclusive level, but for the exclusive structure of finite states. So it's naturally implementable in a Monte Carlo event generator. And I would like to do it in a way which takes into account collinear emissions from the beginning in a controllable way. Namely, it gives a clear TMDlib. TMDlib is the evolution is very good at taking into account collinear emissions. And when doing phenomenology, both with CSS and with BFPL or CCFM, very often we have found ourselves in a situation where there was great accuracy at the high S, or low QT, but there were collinear emissions missing, which would spoil the interpretation of what we're finding in terms of comparison of theory with measurements. So we started to think about an approach which would give you a very clear TMDlib limit, so that we would be confident that the collinear emissions were taken into account in a controlled way with sufficient accuracy. And so this Parton Branching method that I would like to explain the idea of starts essentially with a rewriting of TMDlib equation for ordinary Parton distribution. The rewriting is written here, and if you are familiar sort of with the standard TMDlib evolution equations, something like this doesn't look anything like that. On the other hand, this is a rewriting in terms of this Sudakov form factor and the real emission splitting kernel, which is quite common, not in the details, but at least in the overall structure in parton-shower event generators. So I would like to look at this in this detail and present some results that follow from this rewriting. So, what am I doing here? So I'm considering for the moment just the ordinary inclusive Parton distribution, function of x and mu. And the idea of the Parton branching method is based on the so-called unitarity picture. Namely, if you have a finite resolution in transverse coordinates, so that you cannot distinguish two partons which are emitted closer than a certain transverse distance. By energy momentum conservation, that implies that partons which are emitted near the kinematic limit, which would be 1, near the kinematic limit by an amount larger than this resolution scale Zm, those cannot be resolved. Okay? So, what is done normally in Monte Carlo, you throw them away. You say those partons cannot be resolved. If you just do this naive thing, of course, it's a violation of unitarity. So, how do you restore unitarity? You restore unitarity by a certain procedure, which is what we went through to arrive at this formula. Then the result of this is that you can rewrite an equation which, in the limit Zm going to 1, is exactly the graph. But it's, of course, a different thing if Zm is a finite parameter. And in terms of two objects, essentially. The Sudakov form factors, which is written here, probability of no emission, going from a scale mu0 to a scale mu. And real emission kernels, these are the real emission part of the TMDlib kernel. What's remarkable is that the method works at leading order, next to leading order, even next to leading order. So it's because it's related to general properties of the evolution kernels, which are valid order by order in FS, not just at leading order. Essentially, they are based on certain sum rules, which TMDlib kernels satisfy, momentum sum rules, and they are based on a special structure of singularity in the limit z going to 1, so the infrared emission. So, why is this nice? This is nice because this is an equation which admits an iterative solution, which is sort of sketched here. So you can write the solution of this equation as a sum of no emission for going from this point in phase space to this point in phase space, plus a contribution from one emission, plus a contribution from two emissions, and so on. But then if I have this, so if I construct my solution in this way, it means that I can reconstruct the exclusive structure of the final state. In particular, I can, by transverse momentum conservation, construct what the TMD distribution is from this. My transverse momentum will just be the sum minus the sum of all the transverse momentum emitted. So that's what we do. And so from this, we obtain an analogous evolution equation now for the TMD, which also depends on the resolution parameter Zm, which I had before. It depends on it in a much subtler way, because if you fix your transverse momentum, the structure of the soft emissions is subtler in the sense that if you integrate over KT, you have cancellation theorems between reals and virtuals. But if you fix KT, you do not have those cancellation theorems. So you have a much stronger test that you're treating the infrared properly. And this is sort of a detail in the context of this type of discussion. Yes, it lies in this part of the equation, sort of this part of the equation. Namely, it says that while as I'm doing Parton branching evolution of inclusive distributions, it doesn't matter whether I evolve in angle or mass or transverse momentum. If I do TMDs, it does. And we'll see that in a moment. So the correct prescription is, as people have known for a long time, from the point of view of the infrared structure of emissions, the correct structure is that of evolving in angle. So what do we do with this? Essentially, we do first some validation checks. So we apply this approach to a normal Parton distribution. We compare the result that we get with the evolution. Say we use QCDNUM. This is the standard evolution program for Parton distribution, which is implemented in the XFitter framework. So we verify that indeed, if we take the limit, the resolution scale going to 1, we obtain ordinary D-glap evolution. We verify it at leading order, we verify it at next to leading order, also with very good accuracy over many orders of magnitude in X and in mu. In fact, we are doing these checks at the next to leading order, and that also works. I can show something if privately. Then the other important test is to test the stability with respect to the resolution scale. I said I put this resolution parameter Zm at the infrared end of my phase space. In principle, this is a rewriting which you look at it and you would say, well, this is horribly dependent on what you choose for Zm, because these things have poles at z going to 1, from poles 1 over 1 minus z from emission of soft-gluons. So the check is that although you have these divergences in each of the intermediate steps, the final result does not depend on Zm. And that's the check of the stability with respect to Zmax. These curves, which you cannot distinguish by eye, they just overlap, they're obtained for different values of Zmax. Good convergence, as it should be, if Zmax is close enough to 1. On the other hand, if you're looking at TMD, you see the effect I was mentioning before, that you obtain independence of Zmax, namely a well-defined TMD, if you evolve by angular ordering. On the other hand, if you take a transverse momentum ordering, as for instance is often done in the small x literature, you do obtain a TMD, but you obtain a TMD which is ill-defined because it varies if I change my soft-gluon resolution. It means that I'm not taking into account the infrared logarithms properly, and therefore I change the cutoff, I get a different result. So TMDs can be defined by this approach, provided you pay attention to the ordering in your branching. Okay, so that's essentially the idea and then the gist of the method. So what we've done at this point, we have an evolution equation, this one. It has a structure in which you have a homogeneous term, so the TMD at a low scale, mu0. The kernel are computed with some perturbative accuracy. We work at the next leading order in alpha S, accuracy. So we can compare with data, we can take data, determine, do the typical thing you do with NPDF. From comparison of the theory with data, you determine your input at a low scale. In this case, it would be an input function of x and kt. And then you use that to make predictions for other processes. So we have done this using the precision deep inelastic scattering HERA data. We have determined the starting distribution from data, and then we go and use it to make predictions for instance, Drell-Yan. So we obtain a good fit on precision data. We use the X-fitter machinery, which is a very well-developed, handy machinery. It determines PDFs with uncertainties. So we have an NLO determination of TMDs with uncertainty bands. So in this respect, perhaps I would like to emphasize that it's quite a different sort of spirit from what is often done in the TMD literature. It's a spirit closer to what is common in the community of all collinear PDFs. So one should arrive, I believe, at the point where you have fits and parameterization for TMDs in a library sort of LHA PDF style. We created it in the context of the ref workshop and was termed the TMDlib. And then users would be able to take the TMDs that somebody else has determined from fits, from certain evolution approaches, however they did it. And then you use it in factorization formula to make prediction. This is what is routinely done in the LHC community for collinear PDFs, but it's not what is routinely done in the case of TMDs. So the next edition of the workshop, by the way, is a little advert for it. Be next month. So do I have 5 minutes? Or?
You have about 2 minutes, 5 minutes for questions.
Okay, okay. So what we're doing, we are essentially doing applications of this. The simplest application is to Drell-Yan production, the PT spectrum of Drell-Yan. We see interesting effects in the low QT region. In particular, we see effects of the angular order. You know that the low QT region of the Drell-Yan spectrum at the LHC is one of the most difficult problems. For instance, it's one of the hurdles in a good determination of vector boson masses. And what we find by our method is that the infrared effects, so angular ordering effects, are very important. And so the different curves here, I don't want to get into details now, but different curves show you that these effects are important. Here is essentially the same observable with the lepton pair QT with different, including the uncertainties, the experimental and theoretical uncertainties. We are devoting quite a bit of effort at the moment in comparing the Parton branching method with the CSS method. There are clearly very similar physics in it, so we would like to arrive at an order by order comparison. These are the coefficients A, B, and C which appear in the CSS method. They have a counterpart in the Parton branching method. The expansions in alpha S, they can be compared order by order in alpha S. So this slide is meant to illustrate how we do this, but it's beyond what I want to say in the 30 seconds or so, not left. And the important application we're going to digest, so this is still very preliminary. I sort of motivated this with the case of digest, the case of digest correlation. So we are looking at implementing our TMDs in Monte Carlo, and this is these are predictions which we obtain for the azimuthal distribution, the azimuthal distribution, the azimuthal distance between digits at the LHC. So the curve, the blue curve here, the red curve here is just the Monte Carlo standard next to leading plus shower Monte Carlo, TAWEG. The blue curve is what we obtain when we implement our TMDs. So we implement the transverse momentum dependent factors. And then in this plot, it would be the red curve. From the red to the blue, we go when we, in addition to the TMD, we add what we call a TMD Parton shower. What I should stress is that if you compare PAWEG plus PITIA for this azimuthal correlation, the comparison with data is in fact a bit worse. PAWEG next to leading order plus shower. So we find these results, although they're very preliminary, quite encouraging. Okay, so I'll leave it at this. My conclusions, essentially, what the PB method does, it takes into account simultaneously the QT recoil, that's what NTMDs does, with the QT recoils and the soft-gluon emission. So we find that the soft-gluon emission, one, is essential for realistic phenomenology. So we have, we're doing a number of applications. Perhaps the one I want to stress is that you have the possibility of doing systematic studies of ordering in the evolution and the associated color gradients. Okay, thank you.
Questions?
So, can you say a little bit more about this Monte Carlo with TMDs that you have?
Monte Carlo with TMDs. So what we have at the moment, we don't call it Monte Carlo with TMDs yet, because so what we're doing is we are taking an existing Monte Carlo PAWEG, so that is, and we are using it to generate matrix elements. PAWEG can do it at leading order, next to leading order for a given process, in this case, digest production. And then we have created an interface of this with a TMD Parton distribution. Namely, we take into account the transverse momentum distribution that comes from the initial state. So at this level, it's not yet a shower Monte Carlo. It's a hard matrix element combined with a TMD. What is nice about our method, and I think it's a feature which distinguishes our method from any other Monte Carlo method on the market, is that by construction for us, if you consider the structure of final states that comes from the branch, and you integrate over it, by definition you obtain the Parton distribution. TMD. That's not the case if you take PAWEG interfaced with Herwig or PITIA. In that case, people have never worried about mismatch between Parton shower and Parton distribution. In other words, if you take PITIA and say, okay, I have my emissions, final states produced by shower. Let me integrate over that. Do I recover the Parton distributions from which I started from, evolved by the scale? The answer is no, you don't. So normal Parton shower, don't worry about that. We do, right? So the feature which we like about the Parton branching method is that we circumvent the issue of the mismatch between the shower and the Parton distribution. So for us, the Parton distribution is really what comes by integrating the shower. Being in this situation, then we can add a shower. That's what I do in the next. So here you might call that a TMD Monte Carlo, if you like. Except there are a number of technical issues we have to solve in terms of matching and merging and so on and so forth. So here we have both a TMD Parton distribution and a shower done with backward evolution. So this is the closest to perhaps what you would like to have that we have at the moment. But I stress, so it's first of all, we use PowerWeg. It's an existing Monte Carlo. We just interface it differently instead of using it with Pythia or Herigo, so standard Monte Carlo. We interface it with our TMD. Okay? Which means that we have not looked into the matching issue. As you perhaps know, PowerWeg is user-friendly, but quite obscure in how the matching of the first emission in the shower is done once compared with the Hautmann cell. So we have not looked at those issues yet. And we actually think at the moment that PowerWeg might not be the best choice to do it, just because of how non-transparent it is in the treatment of the first emission. But okay, perhaps what I could stress is that we think the method, the branching method, is a good basis to construct a TMD Monte Carlo, because by definition we started out saying we want to have an algorithm such that by integrating the shower we recover the Parton distribution, which is not what most Monte Carlo. Yes.
Okay, Giuseppe next.
Yeah,
Christoph,
I
and that's
just
it.
to clarify the point that there's the discussion about the soft wide angle divergences. I got series axiom, the paper that you cited.
Yeah.
It was just a comment, not a question.
Yeah.
That paper concerns an extension of the usual soft-gluon resummation formalism that was initially was relevant only for colorless final states, extends this formalism to colored final states, taking into account divergences that arise from the interference of soft wide-angled emissions from both the initial and final states. And these soft wide-angle emissions generate asymmetry divergence that is observed at some specific order in perturbation theory, namely at next equal. So it's not something non-perturbative, it's not something effective theory kind, it's a QCD resummation extended to include the soft wide-angle radiation.
So delta, yes, delta. So this blob here is the soft wide-angle radiation, right? So the reason why, so it's a. So as you see, as this picture suggests, so it leaves. You have this decomposition of the initial state chain over KT. So you have this contribution from KT, which are small compared to 1 over B. Then you have this contribution, which are the KT between of order 1 over B. And then you have the contribution of the KT between 1 over B and the Hart scale. So the wide angle thing that Giuseppe was saying is related to the fact that the gluons responsible for these effects couple these two blobs. So they don't go back to the region of small kt. Okay? So that's why the comment is these are perturbative effects. Okay? Perturbative effects.
Moreover,
So they're related to the. However, this doesn't mean that there shouldn't be also effects which go deeper, sort of backward into the evolution chain, right? And those are the things related to the molders.
Just to finish,
Yeah.
it has to be perturbative because the azimuthal asymmetries are infrared safe observations. The common wisdom is that non-perturbative should not spoil infrared safe observations.
But there is also there are azimuthal asymmetries which you could generate non-perturbative.
Of course, but it's not the case for the process.
Yeah.
Mentioned in the paper that you are citing. We are talking about the production or Z-boson.
Okay, why don't we stop here? Last question by Christoph.
I was wondering if it's possible to study it, for instance, in the W pair production, when one's decaying electronically and the other one decaying into two jets. So if you could, if there could be some implication in this production that can be measured, I mean, at the LHC.
W vector boson, the
Yeah,
double vector,
Yes,
vector boson
for
production.
example.
You mean from the point of view of this?
Yes,
of this?
yes, exactly.
Yes. I mean,
But this can be measured, I mean, in precise way at the LHC. Also. This could be interesting, some interesting effect.
Certainly, yes. Sort of. I mean, the way I see it, I mean, it looks like a sort of a more complicated process, but
the construction is large and there are plenty of events.
Okay, in the interest of time, let's thank Francesco again.